I'll leave him introduce.
Hi, I'm Alex Messina. I'm going to present a piece of my master's research at San Diego State University in the Watershed Science program. I'm going to talk about mapping drought in India with the surface energy balance algorithm for land known as SEBAL to map drought effects in the Krishna Basin. So here's the little introduction, the water balance. You have rain that comes down, evapotranspiration that comes up from the surface, and runoff. What we're interested in today here is evapotranspiration that's driven by the radiative exchange from solar radiation and heat, and we're going to be mapping that with satellite imagery, specifically MODIS. So I'm going to kind of run you through some of the nuts and bolts of the actual process, talk about the data inputs, most importantly how I automated it. That was kind of my main contribution. Then we'll go through some results and the future work I plan to complete for my master's. So just real quick, some of the things that influence evapotranspiration. You have really strong full sunlight, high winds, high temperature, you get a lot of ET. You have calm, cloudy, cool conditions, you get less ET. So we're going to kind of look for those parameters. To introduce the basin here, it's the Krishna Basin in southern India. There's a population of about 74 million. The basin's approximately the size of Oregon, so it's pretty densely populated, but it's mostly irrigation. Only about 1% of the water is used in the urban areas. So it's mostly irrigated agriculture. They experienced a pretty significant drought in 2002 and 2003. They received less than 75% of their average precipitation. And what we want to see is when the basin experiences a big drought, obviously not everywhere is going to experience those effects the same. So we want to see which areas were hardest hit, more vulnerable to drought. You know, is it because they're in a small sub-basin, or is it because they're downstream in an irrigated project? So we're going to look at ET as a means to see what the effects of the drought are. So just real quick, the basic idea is you take a bunch of satellite imagery, you run it through this code that I wrote in Python. It's about 1,700 lines. It does a bunch of map algebra operations where it basically does math on each pixel of an image. You get your output, a 24-hour daily ET image, and then we can do all sorts of analysis on that. So the SEBAL solves the surface energy balance equation, finding ET as the residual. So you want to figure out net radiation, Rn, how much energy comes in, and that's partitioned into energy that heats the ground heat flux G, energy that heats the air is sensible heat flux H, and then whatever's left over is used to evaporate water. And so it calculates all these things from remotely sensed imagery, which is really helpful when you don't have any ground measurements. In this case, we couldn't get any canal flow data or stream flow because it's politically sensitive. They're fighting over their water rights as well. So this was pretty much the only approach that we could use. And the phenomena is pretty widespread. It's over the whole region, so this certainly helped. The main assumption of this model, and models like it, are that ET cools the land surface just like sweat cools your skin. So we're going to use land surface temperature to see that. And the thing that's unique to SEBAL is that it scales those ET values between a completely dry pixel where there's no ET and a completely wet pixel where there's 100% ET. And how you find those pixels is kind of the crux of the model and my contribution to the method. The data inputs are mostly MODIS satellite imagery. It's at 1 square kilometer. It's low spatial resolution because it's surface temperature. You get a wide field of view. Also, albedo and NDVI comes from MODIS. And for the shortwave radiation and longwave radiation, we use GOES satellite surface radiation budget data. And that's at 1 degree by 1 degree resolution. So there's a bit of a spatial mismatch in the data. And so it has to be interpolated. Then there's some other ancillary data, mostly wind speed from the single meteorological station data that was available to us. So how does SEBAL work? Basically, you solve the net radiation, sensible heat flux, and ground heat flux, finding ET as the residual. So for net radiation, you need albedo, shortwave, and longwave. First you solve for albedo, which is a fraction of black sky albedo under direct insolation and white sky under cloudy conditions. And that's solved through this equation. So you have your black sky albedo from MODIS, your white sky albedo, a diffuse fraction from the SRB, which is interpolated to match the resolution, and you get your blue sky albedo, which is albedo under actual conditions. Using that, albedo image, then we take the surface radiation budget data, interpolate that, matches the spatial resolution, and using all those, we have all the parameters to find net radiation, and there is your map of basin-wide net radiation. And this is what really drives the ET process. It provides all the energy to evaporate the water. So now we want to solve for how much heats up the ground. That's a function of how much energy comes in, how much is reflected away. We solved those in the last step. So now we need land surface temperature. Since land surface temperature is also cooled by going up in elevation and the lapse rate, you have to correct it with a DEM to make it like the basin is completely flat for the model state. And then we also need the vegetation, because vegetation shields the ground. So it takes the raw satellite imagery, it projects it, it subsets it, and then it scales it to the correct values, all automatically, so that I don't have to do it, because there's about 130 images to process. And you only have 2 years to finish your master's. So here we go, we have our map of how the ground is heated up. You can see the water bodies are quite cool, they don't absorb the energy as quickly. So now we have G. Now we need to find sensible heat flux. Sensible heat flux is kind of the tricky one. You can't measure it directly with the satellite because it's kind of more a property of the atmosphere. It's hard to tell. So it's quantified by the density of air, specific heat of water, and then the aerodynamic resistance to heat transport. Basically, how fast the air can move heat away from the surface. That's RAH. And delta T. What's the difference in temperature from the surface to the air? And that will tell us how much heat went into the air. You can imagine if you're standing on a nice green golf course, it's cool. If you're on a black asphalt pavement, it feels very warm because there's a lot of sensible heat flux, LAT. So to solve for RH, we take one wind speed measurement from the one meteorological station we have, extrapolate it up to a boundary layer, and then redistribute it to every pixel in the basin based on their surface roughness of the vegetation. So we take our surface roughness, calculates the friction velocity, and finally the aerodynamic resistance to heat transport. Now to solve for DT, this is really like the tricky part of the SEBAL method. You have to find 2 pixels, one that's completely dry, one that's completely wet and evaporating, where we know what DT is, and then we can find DT for all the other pixels based on that linear regression. So we know that sensible heat flux at the dry pixel is equal to the net radiation. We already solved for net radiation. And at the wet pixel, ET is equal to net radiation. So if we can find those 2 pixels, we can find all the rest. So to find those 2 pixels, you used to do it manually. I wrote a code that takes the maximum land surface temperature pixels, and then out of those hottest pixels, it takes the ones with the least vegetation, and it says that that's the dry pixel. It does the exact opposite to find the wet pixel. So and it does all this automatically without you having to go in and say, I think this area is dry, I think this area is wet, like you used to. So you take all these parameters from the dry pixel, and we're going to use those to develop that regression equation by solving DT only at that dry pixel, the only pixel that we know for sure what it is. So you extract the information, and it calculates that regression equation. So you could basically assume that every pixel in the whole image is on that